Ever wondered why a jumbo jet can soar through the air as effortlessly as a bird despite its enormous weight? Is it magic? Or is it some kind of technological trickery? No, it's actually all down to the captivating science of aerodynamics. It's the study of how air flows around objects and the forces that this flow generates. It's the reason why birds, planes, and Superman can fly. Well, the answer lies in the magical world of aerodynamics. The key to understanding flight lies in the aerodynamic profile. So, what exactly is an aerodynamic profile? Well, it's a surface designed to aid an aircraft's lift, control, and propulsion by interacting with the airflow around it. Some well-known aerodynamic profiles include the wings, the horizontal and vertical stabilizers, and the propeller blades. Each of these components has a unique shape and purpose, working together to keep an aircraft aloft and on course. For example, the wings create lift, while the stabilizers keep the aircraft balanced and pointed in the right direction. Beyond these basic components, there are also control surfaces, like ailerons, elevators, and rudders, that form part of different aerodynamic profiles. These can be moved to change the shape of the aerodynamic profile and the forces generated by airflow on it. This gives pilots the ability to maneuver the aircraft and control it during flight. The shape of the wing can also be altered by raising or lowering flaps to provide better low-speed characteristics during takeoff and landing. In essence, the aerodynamic profile is all about managing the interaction between the aircraft and the air around it. The right profile can create lift, provide stability, and allow for smooth, controlled flight. So, the aerodynamic profile is essentially the shape that allows an aircraft to interact with air in a way that enables flight. Now, how does this aerodynamic profile produce lift? Well, let's dive into the fascinating world of physics. There's a principle called Bernoulli's principle, named after the Swiss scientist Daniel Bernoulli, who discovered it in the 18th century. Essentially, it states that as the speed of a fluid, in our case air, increases, its pressure decreases. Think of the air flowing over the curved top of an airplane wing. It travels faster than the air underneath the wing, which takes a shorter, straighter path. According to Bernoulli's principle, the faster-moving air on top creates a region of lower pressure. Meanwhile, the slower-moving air underneath the wing exerts greater pressure. This pressure difference generates lift, pushing the wing, and thus the airplane upwards. So the shape of the wing, or its aerodynamic profile, manipulates airspeed to create different pressure zones. This is how an aerodynamic profile uses airspeed to create lift, the force that opposes gravity and keeps the plane in the air. We've understood lift, but what about the airflow around the aircraft? Well, the model of airflow around a flying aircraft largely depends on the aircraft's shape and its attitude relative to the free airstream. It's the relative speed of the aircraft and the air that matters, not whether the aircraft is moving through the air or the air is moving around the aircraft. Either approach gives us the same answers. Various factors play a role in determining the characteristics of the airflow around the aircraft. These include the size of the aircraft, the shape of its wings, and the density and viscosity of the air. Each of these elements plays its part in shaping the airflow. In essence, the way air moves around an aircraft, dictated by its aerodynamic profile, is crucial not just for achieving flight, but also for controlling it. So the way air moves around an aircraft, dictated by its aerodynamic profile, is crucial to achieving and controlling flight.